This was supposed to be a simple experiment that is now turned into something more spicy. This is a very simple premise. I have two Wemo outlets. Recently, I decided to purchase a couple of these thread-based ones. The thread-based ones are a marked improvement over the Wi-Fi ones, which I think I'll talk about that more in a separate video. What I was really curious about, especially with these types of devices, is just what's the quiescent power draw? Like when these things are not being used, how much power are they using? With the Wi-Fi one, I was able to actually measure that just using a standard inexpensive wall plug through power analyzer. And it would give me maybe like about a half a watt to 3/4 of a watt when it was just doing nothing. And when you turn it on, or it was powered on, that went up a little bit. This I can't measure on any of the analyzers I have. It's below 0.5 watts. It just doesn't show up. It doesn't even show up as any current being drawn. So it raises the question, how much current is it drawing? What's the power consumption difference between these Thread and Wi-Fi powered ones? Because one thing I don't like about smart home devices is when they consume significantly more idle power. Obviously, they're going to have to consume some amount of energy when they're not being used, but if that can be as low as possible, that'd be awesome. So let's find out. I'm first going to start with the Wi-Fi one. I'm just going to say right off the bat, do not try this at home. What I have just off to the camera here on the left is an outlet, power strip, taped down right now, but a power strip, and that is plugged into a separate breaker box that has a 7 amp breaker. Then that goes into a GFCI. This is pretty well protected. Just gonna take these two clips here, gotta move this Thread one away, and we're looking at the Wi-Fi one first. Let's make sure all our meters are gonna stay on. This one will stay on much longer. On the left here, you'll see the voltage, and then this will be the current that's being drawn by the device. We won't get power factor here. I might do that in a separate video with more smart devices like smart bulbs, other things like that. But for right now, I just wanna know how much current is being drawn. But we're just gonna get VA. We're just gonna get volt amperes out of this right now and see how much less power it's using. Editing note here, I just want to make you aware that I erroneously say energy and power a whole lot during the rest of this video. And what I really mean is apparent power measured in volt amps. That's what I meant the whole time, despite not saying it correctly at all the whole time. This is expressed as the absolute value of S as equal to the square root of P squared plus Q squared, with the result including both active power, P, and reactive power, Q. This is an important distinction because what the electric companies measure is P, the active or real power, and we are measuring the absolute value of S, which contains all of it, both real and reactive power. This will be covered in more detail in a future video. Okay, back to the regularly scheduled program. Both of these are ones I actually use. It's not just something that's like I'm taking it out of the box and it's just sitting in its uninitialized mode. Both of these are connected to my home network. So let's start with the Wi-Fi. I'm going to do two things. I'm going to connect it first, but we'll do two tests. One where I power it up and we're just going to see what it looks like idle. And then I'm going to control it from the network to turn it on. I could do it by clicking it, but I want to just show that it's actually connected to the network and I'm not just pressing the button. We'll see what the idle power draw is and the when in use power draw with no load on it. Putting a load on it isn't going to change that's just being passed through across the relay. So let's go. Got everything connected here. Nothing's really changed. I'm going to plug it in and we see what we get when we plug it in. 6.8, 6.7 milliamps, and it is going to start blinking amber white on this one because I don't allow them to connect to the internet, so it's going to be unhappy with that. I'm sorry, just amber, on and off amber. That just means that it's not connected to the internet, which I don't allow it to do. The Thread ones, they don't connect outside of your home Thread network. That's all routed through something separate, topic for another time. But this one is now just sitting idle, drawing about 6.8 milliamps at 120 volts. That's 0.82 VA. Let's go ahead and I'm going to tell it to turn that switch on. There it goes. And we've come up from 6.8 to 11.1. So when it's running, we're at about 1.33 VA, not watts, but VA. Interesting. let's shut this one off and shut it off. We'll go back. So we're at 6.5 and let's unplug this circuit. Then I will switch now to the Thread one. I have a feeling it's gonna use a lot less power because you're not running a whole Wi-Fi radio. It's a much lower power radio. Let's plug it in. Wow. Remember, we were at 6.531 milliamps. We are now at 2.221. And let's remotely turn it on. Okay, 12.45. Okay, 12.2. It's coming down a little bit actually. 12.2, 12.1. We're going to keep it at 12.4. So interesting, the current consumption. So again, we're talking VAs. So let's do a quick calculation of each one of these. So what have we learned? Well, the Thread Wemo uses a lot less energy when it's idle. It's actually 66% less energy consumption, which is, it's amazing how efficient it is when it's just not doing anything. It's only using 0.263 VA. How much power that is, we'll have to figure out once we are able to determine the power factor. Interestingly, when the Thread Wemo switch was turned on and it was then, the relay had closed and it was powering a load, even though there was no load connected, but just had closed its contacts, it was using more power, about 13% more. Now, that to me, it's interesting, but honestly, in the operation of something, with my use case, they're going to be off most of the time. And the ones that have really small loads on them, like lamps and things like that, it's still just a little bit more that's being added on to the total load when it's being operated. But then when it's off, the idle power consumption is just so much lower. Anyways, I hope you enjoyed the video. If you did, please like and subscribe, and I will see you in the next one. Take care.